Good morning, good afternoon, and for some of you, good evening. It is our pleasure to welcome viewers from across the globe to the first session of ArmMotus Academy Fall Webinar Series. My name is Chenon, and with me, I have Sarah Lim. We'll be your host for today's session, and we are very excited to present to you our first ever webinar that involves the topic of the journey from prototyping to commercializations of rehabilitation technologies.
Thank you, Chenon. So I'm so excited to be hosting with you today as we enter into our final webinar series of the year. So we have gathered all the feedback that we had from our listeners and have lined up an exciting theme this time, where we get to hear success stories from entrepreneur come academics.
Without further delay, let's welcome our speakers. Joining us our panel today, we have Professor Denny Oetomo and Dr. Arno Stienen. We'll introduce each speaker in more detail before each of their presentation. And as a reminder, we'll leave the Q&A to the end. Please type any questions in the Q&A box below, and we'll try our best to get our speakers to answer them live.
So first up, we have Dr. Arno Stienen. So Dr. Arno Stienen received a Master's in Mechanical Engineering from the Delft University of Technology, and further received a PhD in Rehabilitation Robotics from the University of Twente. His work relates to the advancements of biomechatronics and human-robot interaction. So he has a proven track record of cross-functional, iterative collaborations to resolve complex problems and has demonstrated the ability to develop and commercialize robotics solutions. So he's famously known for his works on upper extremity exoskeletons. So amongst the devices that were commercialized from his lab is the ArmMotus. So when not working, so Dr. Stienen enjoys spending time with his family in the Netherlands. So I shall pass the floor to Dr. Stienen.
Thank you very much. Let me share my presentation. Just looking for a quick confirmation from Sarah that everything is working. Perfect. Okay, welcome everybody. Today we're going to talk about the challenges in prototyping, challenges in the process from prototyping to an actual product release. And both Denny and myself have experience with multiple devices going into actual production and being sold to clinics for use with patients. So we want to share some of this with you. So I'll start first. I both have some perspectives on the academic and industrial side on technology research, product development, and regulatory approval. And then he will give some excellent additional perspectives, plus the example of a recent tech transfer. So the objective is to do this, to share my personal experiences as a introduction for master and PhD level engineers to better understand what it is to have your products, have your devices out there in the real world and what it takes to actually get there. But I do have to make a disclaimer, these are mostly my own experiences and I'm not an expert on IP or regulatory processes. I'm effectively a user who has worked with experts on these different processes. So whenever it becomes important, consult the relevant expert for advice on your own situations. So the content for my presentation is first share some personal experiences, then some models, development models that can be used, and finally to really illustrate what the product development process looks like. So my own personal experiences is that back in 2004, we were looking for a device that could support the arm against gravity with as little interference as possible in the horizontal direction. Such a device was not readily available, so we developed our own. And this device we used for our own research with stroke patients to see what the effect is of weight compensation. But at some point, Gary Colombo from Haucoma saw the device and said, you know, we kind of want to use this device. So we had used it already, of course, with some software, for instance, this gaming platform on a touchscreen TV. But then it was commercialized. And as you can see, that the prototype that we developed in the university is in essence still the same as the later ArmMotus on the right-hand side. But when looking at all the details, you can see it's a far more professional device that really has the feel that you can actually use it in a clinic. Gaming software was updated and integrated with the other ArmMotus products. There's a webcam in the top, there's better sensors integrated everywhere. But in essence, the technology is still the same. The other device where we actually patented some of the technology was the DEM-based exoskeleton. And it had two remarkable features. The first one was that we could decouple translations and rotations to have a much more comfortable interaction forces. And the second one was that we used dynamic disc brakes to remove energy from the system passively, so safely, but still give the patient a strong workout. You can see the first movement of the exoskeleton in the top. And as you can see, and especially if you look at the shoulder position, it is really a quite comfortable movement with a large range of motion. You see the additional structure in the back that aligns the exoskeleton with the human shoulder joint, and that gives it the freedom of movement. So those two ideas, the decoupling and the adaptive braking, were patented back in the days. I do have to say that after a few years and some explorations with some companies who could potentially use it, both patents were not continued. So after a few years, the patents actually expired. After my experiences in the university, I moved over to Motec, and Oetomo joined the DIH group soon too. And I became responsible for all the devices in the upper extremities, the lower extremities, and the research devices. Through these product development efforts, I saw a lot of what the different expertises within Oetomo and Motec brought into the product development. It's not just simply engineering to resolve some technical challenges. It really is a concerted effort by several experts. So if you look at the development models, what you can potentially do to actually do development, of course, everybody will be taught the standard waterfall method. You go from requirements, you go to design, you work towards implementation, and then you go to verification, and then you have the maintenance steps. And every step you effectively pass it on to the next process, and that's it. It's a very easy method to actually teach, but it's not really what works in the real world. Nowadays, coming from software, the agile model is far more popular, where you start with a concept, you actually create the device itself, you do an iteration, you release it to the audience that want to use it, you do the maintenance, and then you see what it does in the field, and then you go to the next iteration. And slowly, by adding function and function, does your product become ever more useful. You do this in multiple, what they call sprints in software. Of course, with hardware development, you always have a wait time until your hardware, which you want to have machined, is back. But in essence, the process could work the same. This also works quite well. And some smart people have discovered that, you know what, if you actually set it out against two axes, on the one hand, do you have clarity on the requirements in the vertical direction? And on the other hand, we have clarity on the technology on the horizontal axis. Then if both the requirements and the technologies are clear and known, you can still use the waterfall method to actually do product development. However, when it becomes more challenging, or you don't know exactly what the technology will look like, using an agile method of slow incremental, fast but incremental product improvements might become the better option. And then you also have Scrum and Kanban, which is a more advanced method of the agile methodology for when the requirements become really unclear or the technology unknown. Again, all of this is for a lot of different types of developments. More recently, there have been some promotion of the design thinking methodology, and really a non-linear 5-stage process where the same components are in there as in a waterfall. However, you can iterate through them in a much more non-linear way. So you first empathize with the subject to see what his actual problems are. You define those problems, you ideate to create a solution that actually is built in a prototype, and you test it, but you can switch between the different stages in any possible order. So summarizing, Agile's approach that works towards problem solving. Design thinking is an approach that helps towards problem finding, because you often go back to the emphasizing step and defining what your actual problems are. When you look at this from a product development process, it's not just sufficient to have a prototype, you actually want to have a product that the patient can use, and that requires a couple of more steps. So a company called Topstart made a couple of nice slides, and I adapted them, but I do want to give them credit. So wherever you see the logo in the top right, the purple parts are from them. Actually, the steps are fundamental research in academia that with tech transfer to industry to do product development and get regulatory approval. However, academia, again, probably more clinical academia, is needed for the clinical acceptance. Then with reimbursement agreements and sales and marketing efforts, is the product actually ready to be sold and used by many patients. So the focus for today is on the first half, and let's start with the first one, fundamental research. Now in Europe, we've been given an additional challenge quite recently with the adaptation of the MDR, the medical device regulation. This has changed the prototyping process in the university, at least if you want to use it also with patients in your nearby research clinical setting, research clinical hospital. For instance, if you now want to do a experiment, you have to go through the regulatory pathway for clinical investigations to see if your device actually requires additional documentation. So a very simple one is, in step 1, does the device bear CE marking as a medical device? If yes, okay, is the medical device used according to intended purpose? Yes. Is the clinical investigation part of the PMCF, post-market clinical, I forgot the word, abbreviation, of the manufacturer? Yes. Does the clinical investigation involve invasive or burdensome procedures? Yes, then you go to clinical investigation, but no, it's not a clinical investigation within the scope of the MDR. Most often though, as a prototype, it doesn't have CE marking, so you go to the step no. And is the clinical investigation conducted for conformity assessment procedures? This means, is it to actually test that your prototype is ready to go to the market? And because I said prototype, it's already by definition a no here, because you cannot do the assessment purposes with a prototype. So no, it's still a prototype. Are the study subjects subjected to a procedure or required to follow rules of behavior? Now, if you do a pilot experiment, you probably say yes, and then you see you have to follow Article 82. However, if you do initial clinical testing just to see if the device even fits on the arm or can be used without any procedures for strict requirements, then no, it's not a clinical investigation within the scope of the MDR, but yes, you still have to follow some rules. So this looks like these steps. You have a multi-stage procedure for clinical study with novel medical technology. The first studies you do, so you have a prototype that you've developed, is to look at the technical basics. Is the device even fitted on the patient? Does it provide some forces? But you do not look at the effect on the subject at all. There's no, clinical identification, there's no clinical training. This is not within the scope of the MDR. Of course, you still have to make sure that it's a safe interaction, so you need to test this extensively with healthy subjects first. Then you want to do a pilot feasibility study to test the planned study design with a limited number of test subjects. Here you use a more advanced prototype, perhaps one that already learned from the first experimental studies, but it's still possible that you will make some modification to the design to actually learn from this pilot feasibility study. So as long as it's not the final device, the clinical data obtained from pilot studies are unsuitable for the purpose of CE authorization. However, it is within the scope of the MDR, so you have to follow Article 62, 74, or 82, and you have to write an investigative medical device dossier in Europe. And the final step, and the largest step, is conducting the pivotal studies with the final design of the medical device with a larger group of patients. And this often uses the more final device and can be part of the clinical evaluation documentation, and as such is within the scope of the MDR and the IMDD. So really you have to build it up in multiple steps to actually comply with the MDR. Now, if you look at these 3 steps, then potentially there's a conflict with the agile and design thinking methodology. Because if you look at those 2 later processes that I described, you do a lot of iterations with slow growth of new features. And if each time you have to go back to the first steps and get MDR approval, ethical approval for your experiments, it's going to take a long time. So here, there's a couple of challenges caused by the MDR, which means that you have to really think about how am I going to approach it, when will I stop using the design thinking methodology and go to the more conventional clinical testing. So when you're doing fundamental research and you're looking into patient experiments and getting patient data, it's also the time to patent novel innovations. And the reason is as follows. Not only does your invention need to be novel and involve an inventive step, so really make a step over what's currently out there, it's also required that you are the first person to file the application to get the patent, even if somebody else invented it already. And if the invention in any way becomes publicly available before the patent application was filed, the application will be rejected. In the EU, in the US, you have a 1-year grace period between publication and application, but that doesn't mean you can still patent it in the EU. This is a strong one. So if you ever, in a worldwide scenario, have an idea that you think could be worth it to patent in Europe, as soon as you publish it, it cannot be patented anymore. So keep this in mind and ask an expert for the right approach in your situation. So then you go to product development, the tech transfer to industry. So there is something that already has many components of what the final product should have, but it is not a product yet. And the reason is quite simple. In a company, a medical company, you more or less have to work according to the ISO 13485 procedures. And this is not just a method that you have to follow, it's also a method that gets evaluated yearly at your company to see if you really do work as you said you have worked. It's similar, by the way, not just in Europe, but also for the FDA or for Brazil or anywhere. They will come to you to see how your processes are implemented. And unfortunately, they do not always agree on how you should do it. So sometimes you have to be smart about how to resolve conflicts between the FDA and the MDR methodologies. The ISO 13485 standard describes how you should do it, but there are lots of other requirements and standards that look in far more detail in what's going on. And those standards, for instance, are the 14971 on the application of risk management to medical devices. And there's FDA components that need to be met. And this is a little bit an old diagram because it's still the MDD, but now the MDR has components that need to be met. And to help you with this, you have to follow the 6601 standards, which have a lot of subsections. And everything, if you build software, it has to follow the 62304 standards. And everything has to not just follow the standards, also must be tested later by external testing agencies. So this is all needed to actually build a product. And it has a consequence, because the prototype that you build on the university often doesn't follow everything. Of course, there's a good intention. MDR also requires you to have a quality management system, but still the full application of all these standards requires expertise that's not necessarily readily available within an academic setting. So if you follow the 6601, just as an example, the 6601-1 has the general requirements. But then there are on specific technologies, there are collateral standards. For instance, on EMC and X-ray and usability and alarms. Sorry, these are not technologies, these are components that you have to meet. And then you have the particular standards if you use technologies like electron ACC or therapeutic X-rays with additional standards that you have to meet. And if you look at the entire family, and this is just a small section, there is a lot of different standards that you have to potentially follow. Of course, if you make a rehab device, probably the standards on MRI or X-rays are not applicable to you. You never know, maybe you have something that you have integrated. So not everything is relevant, but you need to figure out yourself as a company which ones are, and you have to meet those standards. So what do you need to do after you've got the prototype? You need to partially to fully redesign it to comply with the 13485. This means that you have to do documented risk management performed by a qualified employee. The design process needs to be according to recognized standards. The software needs to be written according to the standards. You need to do elements such as choosing part suppliers according to your standards. If not, every part that comes in needs to be tested for compliance, and the product still needs to be cost effective to manufacture, install, and support. That's why often with tech transfer, you see a quite significant redesign of the product itself. And most hardware requires external 60601 tests, which are expensive to do by an external certified body. And the final step for now is the regulatory approval, and this is just a mention of what you need to do, but the intended use need to be supported by clinical evaluation, and this is quite extensive and quite a bit of work. So only after you've completed all the technical and clinical documentation can you then go through an audit by an external notified body and get your certificate. Currently, we actually think that the MDR is harder to achieve than the FDA approval, and most notified bodies in Europe are swamped with work, so there's quite a bit of delays there. Regulatory approval in many countries is similar to MDR or FDA, but local interpretation can vary widely. So to close off, if you look at when do you actually need money, if you start doing the actual prototype development and engineering, you've got the hardware cost, so there's a jump in capital that you need. And actually, when you start doing the clinical research, you need to pay for multiple devices, you need to pay for the clinical expertise to do these studies. But there's two major parts where you need a lot of money, and that's also where you see the two valleys of death, where after the fundamental research, you get one valley, but then you got regulatory approval, but you haven't gotten clinical acceptance yet. You got another valley of death before you can actually get reimbursement agreements and effective sales and marketing. So in the entire process, you will see that product development requires a lot of experts from production and construction who have to do the actual building, the product manager, of course, the sales input, what gets sold, the software development, the purchasing is essential, marketing for the right story, the clinical research for the clinical evaluation, everything needs to be managed on quality, and finally the clinical application also does a lot of the training of the end users with the device. There's a little bit of a diagram because that's interesting for the slides from T-top start that can potentially help you in some of the steps. I'm not going to go over it. It's just there for potentially inspiration. And that is actually the final slide of my presentation.
Thank you, Dr. Stienen, for sharing this very inspirational success story on the projects and some of the useful framework that you share in the medical device development. I think those are very useful for a lot of people and especially for our audience here. So next up, we have Prof Denny Oetomo. Prof Oetomo obtained his PhD degree in mechanical engineering from the National University of Singapore in 2004. He joined the Department of Mechanical Engineering of University of Melbourne, Australia in 2008, where he is currently a full professor. His research interests are in mechatronics, robotic manipulation, and human-robotic interaction and collaboration, with applications in healthcare and industrial tasks. He has a proven track record of industrial university collaborations with multiple projects to solve current industrial obstacles, as well as to achieve technological transfer. Outside of research and university work, Professor Oetomo loves to spend his free time walking his dog in the park with his children in Melbourne. I'll pass it to you, Professor Oetomo.
Thanks, Shannon. Can I also check that the screen is showing the right window? Yeah, it's... Yep, thank you. Thanks for the introduction. Thank you for having me, everybody. I am very honored to be asked to give this talk on, to share my experience on my journey to commercialization. Again, just like what Arno said, I'm not an expert in patent or even an expert in commercialization. We do utilize a lot of the university resources that are available to us. And I will just simply be sharing my experience in this. A quick disclosure, I'm obviously, given the title of the talk, I'm one of the inventors of the products discussed that has been commercialized and may one day see some sort of financial gain from it. So I'll say that up front. Okay, what are we talking about? It's nice going second. Arno has covered a fair bit of what we're talking about today. I will try to complement what he said, especially from the academic point of view. I'll start with the generation of intellectual property in academia. I guess outside of teaching, the whole business of academia revolves around generating academic output or research outcome. And they come in several forms. You can have publications, design, monographs, books, and one of those patents. We probably rarely hear about it, I guess, in the more general sense. We always hear about papers, publications, but of course, something that is potentially with the potential of generating commercial outcome should come into the consideration as well. So the focus of my talk will be, we will not be talking about other types of IP such as publication, but we'll focus on things that goes beyond academia, usually that goes into the commercial world and something with commercial potential. That usually comes into two forms. Generally, you have something that is protected or patented, and you have the general know-how that gets transferred into the industry that doesn't get disclosed to the public through patents. And as Arno had mentioned, obviously a lot of people know about this, but you should be careful to check your publication plans when you work through your research. And if you find something novel that you think could be of commercial outcome, you should probably consult your institutional IP experts. Generally, what is already in public domain may or may not be patentable in certain areas, such as in Europe, as Arno pointed out, but it doesn't mean that you can't publish and patent. You just have to get the timing right, and the important message is you should consult your institution expert before you publish. Move. Just a quick mention of factors in decision to patent. Obviously, for something to be patentable, it needs to be, as we mentioned, novel, useful, and not obvious to other peers. But even if it is patentable, it doesn't mean that the university is keen to go into the journey of patenting something, right? There is, of course, the cost itself to patent that could be quite significant, and depending on the regions that you seek protection on, that costs could go up to a significant amount. The university also would like to assess the potential of return on investment. That's a very important consideration. It could look at the potential market of the problems that you are addressing with your patent. The larger the size, the larger the potential, but not just that. They also would like to, given the fact that the nature of our work in academia tends to be fundamental research, a lot of our outcome could be applied to many different applications in different scenarios. So they tend to want to have slightly more mature proposition of how this patent is going to be used, or which specific industry, which specific sectors, or even specific product or markets. And that's where the last point comes in. If you have a commercial entity that's already interested to support your idea by providing some sort of assurance to and declaration of interest to the university, that they would be more likely to be interested to support your patent. With that, I'll jump into the example itself. So that's from my personal experience. This is one of the robots that came out of the research, fundamental research conducted in the laboratory. The process of designing a robot itself started in 2016. It is an upper limb assistive robot, typically used for rehabilitation, but of course it can also be used to assist physical tasks in non-clinical applications. In 2016, we were looking for something that could do this design brief. Obviously, there were a lot of solutions out there. We tried a couple of robots, which we didn't find to be exactly satisfying the brief that we needed. We then also worked with the Royal Melbourne Hospital and a few other institutions around us to look at the needs by the clinicians. And we came up with a design brief, which we eventually followed in 2016. For those of you in the rehabilitation robotics field or familiar with this field, the design brief is probably not too unfamiliar. These are pretty familiar requirements. We would like to have a robot that is reasonably free for movement, with reasonable workspace, fitting the upper limb, allows exploration of different postures during a task execution, specifically for reaching in this case, capable of weight support and interaction with physical object, and practical considerations such as compact footprint, quick setup, and be integrated with other relevant sensors. I was looking at Arno's presentation earlier, and I thought, well, you know, we could have used each other's robots actually. And but anyway, this is what we ended up with. I will just play the video to demonstrate what it does. The design was patented before it was reported at I-Core in 2017. This was the first prototype. As you followed Arno's talk on the journey, this is our journey where we started with prototype 1. You probably noted that this is a pretty basic prototype, and this is showing how it can, you know, it has low inertia and friction, yet capable of carrying, you know, significant, or not significant, a reasonable amount of load. You can probably see that this is constructed out of wood. It was simply done to verify or validate some of the kinematics that we wanted to attempt. Most of it is out of MDF and bits of aluminum profiles. The motors, obviously, real motors, and they're capable motors and controllers, power supply, but you can probably see the IKEA furniture legs there as well that we use to very quickly set up what we need to construct the prototype. From that point on, we went on to a program that the university set up to train academics to be more familiar with research driven by end user needs. That got us through a lot of needs validation, developing various prototypes along the way, 2017-18, user studies, before we went into come into contact with our industry partner Fourier, who decided to take the journey on to further the industrial design and manufacturing. So that's prototype 1, as I mentioned earlier, that was shown in the video. We had the 2017 to, well, mostly 2018, that was used in a lot of the clinical tests. 2019 was a slimmed down design. This was the last iteration before we passed it on to our industrial partner, who then took it on another stage of redesigning for commercial purpose and manufacturability, and that turned out to be quite different, but it looks much more professional, obviously, and also size-wise is a lot bigger than the prototype that we anticipated. However, it looks it works well with the extra weight down the base, which makes it also quite stable and balanced. Right. So in 2021, we were sent this photo by our industry partner, our colleagues there, that showed many robots being produced of the same design, which is quite an interesting feeling for an academic, because we're so used to building one robot in the lab, and that's going to be the one robot that sits in the lab and you write paper on. And it's certainly a very satisfying feeling to have a little production line producing a lot of your design. So I just want to summarize the timeline of how this whole process went. I know this is looking quite hectic. This is just the timeline from 2013 to around about 2017, where we did the fundamental studies supported by the Australian Research Council. So they started off as fundamental research studies, and we needed to have an experimental rig to test our work on human motor adaptation in 2D and 3D space. We started building an experimental rig, which we then further developed with clinical consultation and co-design. And you can see, I'm not sure if you can see my cursor, but I highlighted in yellow the involvement and support of the university, where a lot of development remained within the university. And then you see the green bit, which is the valley of death that was also highlighted in Arno's talk, where we get to a point where we have the 2019 prototype, which was functional and yet not a product, to the end where you get a product at the end. And that's where the involvement of the industry partner came into play, with the university that kindly provided additional support, such as up here, the University Proof of Concept Grant 2019 that bridged us over. The industrial design with Fourier happened in was the second quarter of 2019, and it continued till the release of a product in 2021. Interestingly, our exclusive license to the industry partner was only executed in October 2020, more than a year after Fourier decided to take on the industrial design of the product, which was interesting. It shows a lot of trust in the collaboration between the two entities, which I thought was quite important, because otherwise we would have died in the valley without being able to cross it. I further simplify. This was the two items I highlighted at the top that was, on hindsight, critical in us crossing the valley of death. And simplifying the diagram, I looked at the timeline of patenting, and we started patenting in 2017 after the first prototype was ready and tested. And the provisional patent was completed or expired in 2018 May, whereupon we embarked on filing the PCT, the international PCT. That lasted slightly over a year. At the same time, the national patent was also filed in 2018. So the national is where you apply in different regions, such as the United States, Europe, China, Australia, and they can take a long time, and that's quite uncertain. At this point, we have obtained the US patent recently at the end of last year, but a lot of the other regions are still under evaluation. So looking at this timeline, it is certainly a journey that started in 2016 and patenting process started in 2017, and until now, we are still in the process of getting our patents accepted. So it's a significant investment of time and resources. And I realize why now when I look at the product out there in the market, everything has patent pending on it, because you can't wait for the patent to be accepted before you sell it. I think that would just take too long and no one could survive that. How are we doing with time? I'll be quick just to provide a bit of a perspective on licensing from a university. I would like to probably provide the perspective of the university in this process. The university invests a significant amount of time, resources to support each of the patent they decide to go with. And I think they often see royalties in the license as an investment recovery, and also to fund the subsequent commercialization project. Obviously, they are interested in commercialization, and they're also very interested in firstly the recovery of the investment they make on each of the patenting process, and that works out quite interestingly with our industry partner, for instance, when they try to license this from the university, because as a startup, a lot of companies tend to not to have a lot of initial capital outlay. They do not want to pay for a large sum to purchase or to license the patent initially from the university, preferring to spend the money on design, industrial design and the various other processes to bring the product to market. And that is something that could be a sticking point between two parties during negotiation. And I guess I also point out that the researcher sits in the middle, and it's an interesting role for us to serve, because obviously for us, I'm speaking for myself, obviously. Sometimes we're quite realistic about the potential gain we get from the whole patenting process. And a lot of the time we sit there with our KPIs from the university on having to publish and having to produce research and having to engage with the industries and have our work out there. And the point of view from the researchers is that we would like to have the collaboration to succeed, and we would like the university and the industry to agree on the patent and get it going. So if you're the industry, the researchers are probably people you could that would be your champion to the university to get the process going. The researchers know technically the university would assume that the researchers are in their corner, but as an industry, you probably want to have the researchers in your corner, because they could help you negotiate for a better term. If you want the collaboration to happen, there are ways you could influence the university to in terms of the when you're consulted on how eager you are to push this forward, you have your say on that. At the end of the day, we managed to come to a very agreeable term where the university and the industry share profit when the product succeeds. That also means that the industry doesn't have to put out a lot of money at the start, but the university doesn't or still benefit from the entire arrangement at the end of the day. So that's about it that I have to share, for in this topic. I probably would summarize a few takeaway points. The industry is an important stakeholder in the field of rehabilitation robotics. We often talk about this field as being interdisciplinary, that we need the research expertise in engineering and clinical expertise, patient, clinicians, users. We often forget that there's a third party that is critical in getting the technology out there, which is the industry. Second point is that understanding the IP process and or the appropriate process is important for researchers. We should all know it because it is part of the processes that would allow the industry to commercialize things and eventually get our technology out there for people to use. And the last thing is that without the university and the industry support, it is very hard for us to cross the valley of death. A lot of us academics know that we have a lot of prototypes sitting in our labs, and getting them across the line to become product that people use is a significant endeavor. I'll stop my talk there. Thank you.
Thank you, Professor Oetomo, for sharing your inspiring journey on commercializing the technology. So I believe you've experienced and you went past the valleys of death multiple times, as mentioned by Dr. Stienen. So it really highlights the importance of industry working closely with academia. And I think in your case, it's also with clinical team, for designing and bringing the product to market. So thanks again to both our speakers for sharing your insights and wisdom. So thank you to our audience for your time and attention. So I believe we have been receiving some Q&A boxes in the box below.
Yeah, I think we have also quite a number of questions already. There's a total of 9 questions. And Dr. Stienen already answered a few of the questions already. But we have one good question from the Q&A section. One of the attendees asked, when and how are the patients selected to trial the prototype that we developed? And Dr. Stienen provided a good answer, but perhaps Professor Oetomo, can you give additional advice with these questions?
Look,
Yeah.
I haven't actually read what Arno said,
Yeah.
but I don't
Yeah.
know how much to add. Maybe
Mm.
it's answered it really well. But yeah, patient and what was that again? When and how?
When and how we select the patients for trial, especially for the EMU.
Oh, especially for the EMU. Well,
Mm.
okay, maybe I'll answer it more
Yeah.
specifically. That we have multiple rounds of tests. It's not just one. So at the start, we just had a usability test, and that simply is a test that the device is suitable. You know, it works properly. It doesn't. We're not even testing for efficacy. It's simply that it can be used safely within the scenario that we're looking at. You know, stroke patient. Of course, before that, we're even talking about just healthy subjects to test the mechanism itself to ensure that it works well. So there are multiple stages and different sets of different purpose in each of the tests, and each of them could be a separate project, a separate ethics approval, and within each ethics approval, you have to justify what the purpose of the test is. What kind of patient or subjects, doesn't have to be patient, it might actually be healthy subjects, what kind of subjects you want. And then if it is indeed patient, then you have to get your exclusion criteria and all that. And if it is a hospital, you have to work with your clinical partner on the other side. You have to also get the ethics approval approve or endorse at the hospital as well. And sometimes they might be more strict than the university ethics board. But within that ethics plan, you will have to very clearly state what type of patient you're looking for. And you have to very clearly state your recruitment process, how you ensure that they're safe, how you get their consent, how you reimburse them if necessary, and so on. So there's not just one, but there are multiple stages of doing so.
Thank you, Danny. So I think next, Monica asked a really good question that maybe I'll get Dr. Stienen to read the answer again. So let's say you've published the design that you then decide you want to commercialize already, and then you can't get a patent anymore. So how do you proceed?
Well, you don't need a patent to commercialize. A patent protects you from your ideas being copied by another company. But there's so much previous work out there, and patents can be overly broad or too specific, so you can work around it as an engineer. A patent only gives you partial protection. I think the biggest factors in successfully commercializing your device, and that means that a lot of patients use it, is actually to have a good device, but then also to focus a lot on having an effective regulatory reimbursement and sales and marketing strategies. Those latter are absolutely essential to have your technology being used by patients all over the world. So patents help, but are not necessarily the most important step.
Thank you, Dr. Stienen, for the answer. Maybe we can take one more last questions from the Q&A. I think there are 2 unanswered questions. A question for both our speakers today. So the attendee asked how to better manage the communication between different or many stakeholders in the product development process. Maybe Dr. Arno, maybe Professor Denny, you can start first, and then we'll pass it to Dr. Arno.
I have no good answer for that, actually. I wish I knew. Look, I mean, if you follow many of these design methodologies, you will be asked to identify your stakeholders very early on in the process, but you will still keep finding more and more as the journey goes on. Anyway, I don't think that ends. You always meet new people and new people that can help you. In terms of managing the communication, yeah, I have no good answer for that. That's a full-time job just to be able to get. I know you have a better answer. I'm at a loss.
Oh, I agree. Oh, I agree with your statement. That's a full-time job. I think actually doing really good product requirement finding with stakeholders is a skill, is an expertise that you need to work on. I've had most success by following a methodology where you interview a lot of different stakeholders, write down what they've said in their own words, and then try to translate that to user requirements and potentially later design specifications. But those technical user requirements then become something that you can evaluate, because it's often the case that 2 or 3 different stakeholders say contradictory things. And if you actually have converted their speech into what it means technically, you can then have a discussion. You can then have a user requirement conflict resolution discussion where you agree upon, like, hey, okay, so the range of motion needs to be this, and the device needs to be small enough that it can go home and not just stay in the center. It requires a lot of effort. Luckily, of course, quality management processes are also intended to actually early in the process resolve potential conflicts, because that's the most cost-effective way of doing development. So if you have a approved 3485, for instance, certified quality management system, and you actually follow it correctly, if you then become, if you're at least a little bit cooperative, it should be possible to resolve a lot of the communication challenges. However, it still will always remain a challenge, and the world changes while you're doing development, and later stakeholders or later financing can still change a lot of elements, but at least you've done the utmost what you could potentially have done.
Thank you. So communication is key. Yeah. So I believe we are almost out of time. So thank you, Professor Oetomo, Dr. Stienen, for answering and sharing your insights in prototyping and also product development. So thank you for all your questions as well from the audiences. So if you have any further questions, please email us and we will send them to our speakers today and hopefully get back to you. So thank you for joining us, and we hope that you have enjoyed and learned from the experts on today's panel. So before we conclude the session today, so we would like to bring your attention to this poster presentation. So we also have the QR code that leads you to the registration of our next webinar, which will continue the discussion of how you bring kind of your prototype into commercialization. So thank you for your time. For now, goodbye, stay safe, and we'll look forward to seeing you in our next week as we talk to 2 other entrepreneur cum academics and how they've started their company on rehab tech. Thanks, Arno. Thanks, Denny.
Thanks, Arno. Thanks, Denny.
Guys.
See you.
Bye-bye.
All right.
Bye.
Thanks, folks. See you soon.
See you soon.